Okay, hello students. Welcome to our first lesson on intermolecular forces. So the point of today's lesson is that we're just going to look at the relationship between the observable properties, particularly the melting and boiling point, and the nature and strength of intermolecular forces, including dispersion forces, dipole-dipole attractions or dipole interactions, and hydrogen bonding. And this is within the molar covalent substances. So we're going to look at three types of intermolecular forces, and these are forces that occur between molecules. And as I said before, there's dipole-dipole forces, hydrogen bonding, and dispersion forces. Now don't confuse these with intramolecular forces, so that's within the molecule, so that's covalent, ionic, and metallic, for example. So we are looking at three types of attractions between molecules. So these intermolecular attractions are weaker than ionic and covalent bonds. So 10 to 100 times weaker than covalent bonds, for example. The first sort is these dipole-dipole interactions or attractions. So these are intermolecular forces resulting from the attraction of oppositely charged regions of polar molecules. So you know from last lesson that covalent molecules can be polar, and so the negative end will be attracted to the positive end and vice versa. Now, because the molecules are attracted to each other, it takes more kinetic energy to separate them. So more polar and more asymmetrical molecules they're going to have a higher boiling temperature or boiling point, I should say, melting and boiling points. Now, hydrogen bonds are a special type of dipole-dipole interaction, and this always includes hydrogen. Now, it's the only chemically reactive element with valence electrons that are not shielded from the nucleus by the layer of underlying reactions. Now, what's interesting here is we have a look at methanol and ethane. What do we got? We've got C2 and an O there, whereas ethane, what's got C2H6. And you can see that methanol, even though it's smaller, it's got less molecules, it's got a higher boiling point, and that has to do because of the attractions of the methanol to the other methanol. So remember, we're drawing out partial charges. That's going to be attracted to the other end of one of these molecules. So there's going to be an attraction between them. Whereas the electrons are just all evenly spread over ethane. So there's no real attraction between ethane molecules where there are between methanol molecules. Okay, hydrogen bonding, as I said, is a special type of bonding. So it's a bond between hydrogen and oxygen is very polar. So that's a very common one, but we also have hydrogen bonding to fluorine or nitrogen as well. Now remember, the oxygen is partially negative and the hydrogen partially positive. So as a result, the hydrogen atom on one molecule is attracted to the oxygen atom on another. So this intermolecular interaction is referred to as hydrogen bonding. So this is a special type of dipole interaction. So if we have a look down in the bottom left, first of all, we've got ethane, methanol, and methanol. So what's happening? We've got a bit of hydrogen bonding happening in the methanol. So that's going to have some attraction, so there, for example, between another one of the hydrogens. What else do we need to think about? I think that'll do for the moment. We can also think of this area here as a hydrogen bond between different water molecules, and you can see on the bottom right that there are different dipoles in the water molecule, and there's just these little bonds that are attracted or show this attraction between the water molecules. And this sort of bonding is responsible for surface tension, for example, in water. and that's important to form water droplets. So water is more attracted to itself, so it will form a drop rather than flatten out on the surface of a leaf, for example. Now, if we think about hydrogen bonding in water, it's interesting to note that when water freezes, it becomes less dense. So water is most dense at 4 degrees Celsius. So that's an important point. So if I think about why lakes don't freeze all the way up, they freeze from the top down. Now that means that layer of ice there, that insulates the rest of what's underneath, but when water does go to a lower temperature, it's going to float because it's less dense. So that makes it very important. When water freezes, it floats, and this floating water called ice, it insulates the rest of a lake. So there's going to be, in a frozen lake, there's going to be 3 or 4 degrees Celsius there that life can be sustained at, and you'll learn in a little bit, the cooler the water, the more oxygen can be dissolved into that lake. So it makes it quite a sustainable habitat for some animals. Okay, so the last type of attraction are called dispersion forces. Now these are also known as temporary dipoles or instantaneous dipoles. Now if we have a look at the blue picture down the middle, you can see that electrons are constantly in motion in an atom. And so that means even in something like neon or a diatomic element, so like F2, for example, where there's equal distribution of electrons between the atoms, they are going to sometimes be spread towards one side of the atom, and that will repel the electrons from the other side. So you're going to get this separation, this temporary forming of a dipole in these non-polar covalent molecules. And so that will mean that these atoms are going to be attracted to each other. Okay, so what you can see here is the 4 halogens, fluorine, chlorine, bromine and iodine. They're under each other, and you can see that the molecular mass is increasing, obviously the number of protons and neutrons, but what's important here for dispersion forces is the number of electrons in the atom. And so as the number of electrons increase, so do these temporary dipoles. So the tendency of these electrons to go to one side of the atom and form these temporary dipoles, or these, and makes they're polarizable, I suppose you'd say, is that they're going to be attracted to each other. And so the larger the atom, the more likely these dispersion forces are likely to occur, and that's because there's more electrons, and so that will increase the attractiveness of each of these atoms to each other, and therefore increase the energy required to separate them. So that means that it's going to have a higher boiling point. Now you can also see a similar pattern in hydrocarbon chains. So on the left hand side we've got propane, butane and pentane. So propane's a C3, butane's a C4 and pentane's a C5. So we've got a 3-4-5 carbon chain, and you'll notice that the longer the molecule, the boiling point will increase, and that's just increasing the surface area for these electrons to spread out over the molecule. Now butane and methylpropane have the same formula. They're both C4H10, but you can see the structure of them are a little bit different. Methylpropane is a bit more of a T or a Y shape, whereas butane is a chain. And so the butane, being a longer molecule, will have a slightly higher boiling point because of that. So today we have looked at 3 intermolecular forces. We've looked at, first of all, dipole interactions, and then we've noted that hydrogen bonding is a special type of that, and hydrogen being just having that proton exposed. When it loses that electron, it's got that unshielded electron pretty well. So that's going to form some very strong dipole-dipole bonds, and so that's going to have a special type of bonding called hydrogen bonding. So that happens with fluorine, oxygen, and nitrogen. And finally, we looked at a third type of intermolecular bonding called dispersion, and they are temporary dipoles. So we have three types of intermolecular forces: dipole, hydrogen bonding, and dispersion forces. Finally, you'll notice on this diagram there's an ion dipole. Now, if I were to put salt into water, that's sodium chloride, it would separate into the ions. Now, if I think about that, if there's a H2O, so there's an O and there's a H, what's going to happen? You've got to draw properly. You're going to have that negative end, and so that's just going to be attracted to, for example, that oxygen will be attracted to the sodium ion, and down here at the positive end of the molecule would be attracted to the chlorine. Then covalent bonding, so polar and non-polar, and then the covalent molecular in diamond would actually be over there. Other than that, we've got the ionic bonding. Okay, so we have looked at three different types of intermolecular bonding, and we've related them to the nature and strength of the observable properties, which are the melting point and the boiling point today. When you've done that, it's time for your mastery exercises.